All right. Hello and welcome to this new episode of You Wouldn't Type Check a Car. First thing first, this is the first stream of the year, so Happy New Year wherever you are. Hope you've had a good break and a good start of the new year. Uh, if you have any resolutions, if you have any projects you're working on this year, good luck with that. I have some of my own that I plan to finish. Maybe I'll share some of them at some point on the stream. Uh, I haven't streamed in a while. I think the last stream we had was back in October, and I was taking a break since then. A couple of reasons combined. I had a deadline back in November, which I really had to finish a lot of work for. So I took a break then, and then after that, there was like the holiday season. So uh, I was working on some other things, and then by the time January rolled around, I couldn't force myself to sit down and start stream again. But last week I just decided let's just get back to it. Let's finish this project. Let's do some more interesting projects, and just see how you all are doing. So yeah, the sixth episode of You Wouldn't Type Check a Car today. Uh, to catch everyone a little bit, we are currently working on this NES emulator using Build It. Build It is the project that is the main part of my thesis. It's a compiler library. It's a DSL library. That's how I advertise it. And if you haven't checked it, go to buildit.so. There's a link on the on the screen, and we'll be using that to write an emulator. Uh, so far we have implemented in the first stream we implemented the basic infrastructure for the code generation part. For every instruction in NES, we emulate those instructions using build it and then generate code for that gets optimized with the backend compiler and then gets executed. In the last stream I did something different. I actually just had a silent stream where I wasn't speaking anything. I was just working on the implementation, finishing all the rest of the instructions because there's like 256 of them. We implemented a bunch of those module, like barring a few ones that require changes to how the whole system works. So we'll work on that today. We'll have all our instructions working, and then we will start implementing the logic for loading the ROM, jumping into the right place, setting up all the memory places and everything properly. We'll have to probably look at a lot of NES documentation for that. I mean, NES Wiki has a lot of resources. We'll have to look at the documentation for the processor, which is the MOS 6502 that the NES used. And we will hopefully get to maybe also implementing parts of the CPU, which is always fun, like the actual drawing of the pixels on the screen, the sprites and everything. It's a lot of fun. I've done this project before a long time ago. I think this was like 6-7 years ago when I did an NES emulator a long time ago. But that time I didn't use Build It. I basically just wrote a normal emulator where every instruction generates some x86 instructions, puts it into a stream and executes it. It was fun, but I want to do it this new way using modern compiler technology. So yeah, let's get right into it. If you have any questions, you can drop them in the chat. I'm happy to answer them. I guess we'll talk more about the project as we implement it. Okay. So back to the screen. The repository and everything, the links are posted on the Twitch channel. There's also a resources repository which has linked to all the other repositories that we work on. Any resources that I share while on the stream or anything that sort of comes up in the chat, I paste it there so that we have a record of it and people can look at it later. But getting to the main NES repository, I don't think I have changed anything since the last time we met, except for updating Build It. Build It keeps going through changes. We have new features being added. We have some bug fixes, some sort of like nice changes that I do to keep the code base more efficient and just more clean and so on. So I've just made some changes to Build It, which I have pulled. That's what I did last night. Just made sure that the latest version of Build It works and with the system. So I think we should be able to, yeah, this is done, right? So if I just run the compiler, yeah, it executes and run. What this is printing currently is, if you go to the driver, I have a simple NES program. I don't remember the instruction encoding for these now just because it's been a while, but we can look at what these mean. And then we have basically, at this point, we sort of create a context. We ask build it to compile the emulate code function, which are implemented elsewhere, with this program as an input, and the starting point, which is 0 in this case, because we want to start interpreting the program from the 0th position. This returns a function pointer, which we cast to the right type. This function pointer, then we allocate some memory for the main memory for the program, which in the case of the NES is just 0x10000 amount of memory. I just initialize all the registers, which is a helper function that we have, and then we actually execute the generated code, which then updates the registers or whatever, and then I print them out. So this is a simple debugging loop. We will change this a lot, so we'll move a lot of this into the pipeline today as we work on this. But the main thing that I want to get to, that we sort of left off at last time we were working on this, was the instructions. Okay, so yeah, we have a giant if while loop that goes over that goes over all the instructions and sort of interprets them using buildit. But because buildit is a multi-stage programming library, instead of executing those instructions, it actually generates code for those instructions. So for every instruction, like say branch on not equal, we basically have code that checks if the context flag is 0. Sorry, the 0 flag is not set, and if it is not set, then we obtain the offset from memory where we want to jump. That is the instruction, whatever the instruction encoding says, and then we do a jump to that by just updating the PC. Now all these variables, PC and context.0 flag, these are all dynamic variables, which means that they do not have concrete values in the emulator. They just generate code based on what the operations happen on them. So this if condition basically gets generated as it is in the generated code. And this update to PC actually makes changes to the current program counter, which is in the first stage, and we start interpreting at the new place. So that's like a nice mix of stage programming that generates some nice code for us. I mean, we have talked about this before, but yeah. Yeah. So the thing that we left off last time was indirect jumps. So normally this PC, actually let's go to PC. PC here is defined as a static variable. What that means is in the first stage, in the compiler, this PC has a concrete value, which is initialized to the offset at the start. So that's like where we are starting interpreting the program. And at the end of every at the end of this while loop, the PC is updated to be PC plus instruction sites, that the last instruction that we emulated. But what this means is this PC keeps changing inside the compiler without actually knowing any concrete values for the registers or for the memory or the input from the user or anything like that. This poses a slight challenge. Branches and conditions are fine. Like if we have a condition like this, which we just saw, this BNE, we have a condition on a dynamic variable whose value will only know at runtime. We can update variables like PC, which is known in the first stage. Buildit handles this nicely. It does this by sort of generating a condition in the code, and whatever happens after this PC is updated to this value gets put inside that condition. But this doesn't work if we try to actually do an indirect jump. What I mean is, this supposes BRK instruction, right? Actually, no, BRK is a bad example. Let's look at jump. Sorry. So for example, this jump instruction, it has two addressing modes, absolute and indirect. Absolute is the normal version where you just have the address that you want to jump to as part of the instruction encoding. We load that address from the memory, in this case from the instruction stream, and then just set the PC to be address, and that is fine. That works exactly how we expect it to. But the other case where the instruction encoding is indirect, we actually have to do a double load. So we first get the address from the instruction, then we have to use this address to look into the dynamic memory. So the memory that's sort of at runtime, where the data is stored. It loads the low and high address, computes the return address, and now we need to jump to this return address. We can't do that in the compiler right now because this value is not known. So we actually cannot implement this normally using build it. But one way we can do this is actually defer the code generation or the jump to runtime. So what we can do is the function that we're generating has this interface. If you look at this function that we're generating, it has actually let's go back to start of the function. This emulate function that we are generating has a couple of parameters. So it takes the main memory as a parameter. This is a first stage parameter, so this goes away. The offset is also a first stage parameter, so that also goes away. But it has a dynamic. So by the way, the convention we are following here is any variable type, any type that starts with D implies that it is a dynamic variable. These have been type def somewhere else in the code, so you can't see them. But this is essentially a dynamic pointer to a byte in memory. So also the variables are also I try to name them in a similar way so that we can just like look at the name of the variable and tell whether it's static or dynamic. But anyway, so this function that we will be generating takes in the main memory address and also returns a NES word. So it returns a 16-bit value, 16-bit value at runtime. So what is the significance of the 16-bit value? The convention we're going to follow is that this function will return the address that the execution should continue at. So when the compiler sort of invokes this function, it'll start executing, and it will eventually, suppose it reaches an indirect jump, it will compute the address where the execution should continue at runtime, when the program is actually executing, where the memory, where the registers have concrete values, and it will return that value back. Now at that time, we'll invoke the compiler again to start sort of generating code for the point that we want to continue execution at. So suppose you start execution at address 0, and it continues, and it eventually reaches an indirect jump like so. At this point, at the execution time, this return address will be computed, and we will return it out. So this return address will actually reach here, this ret. But what we can do is, at this point, we can invoke the compiler again. So we can put this whole thing in a loop and say, okay, I need to go to a new address, compile the code for it, and give me a function pointer, and I'll start executing again. And that's how we'll sort of emulate indirect jumps at runtime. This is obviously expensive because running build it, compiling the generated code takes some time. And that's how we'll implement caching on top of it. So we will have basically a map that will keep track of all the addresses that we have interpreted at, have generated the code at, and we'll keep those function pointers around for the execution. So if we ever jump to the same address again, we won't have to sort of recompile the code. In fact, we will do this caching across runs. So if every time the emulator runs, it will keep a cache of code. So across, like, it'll remember basically this ROM, this address, here's the compiled code. And I don't have to like sort of recompile it again. I can just load that from the shared object that we generate. So we don't have to like sort of keep compiling every time. What this also means is once we have run this game, like a particular game enough number of times, we don't ever have to run it like compile it again. We will just have a bunch of C files that implement the logic of that game. This essentially behaves like a normal compiler then, where you take a NES ROM, supply it to this compiler, and if you run it enough, it will eventually produce a bunch of C files that together implement the game logic, and you don't need the compiler on the hot path again. So yeah, let's see how we get to that. I think the last thing we implemented was actually returning out the return address too. So yeah, so at the indirect jump, what we basically do is we sync out the registers. So we have a local copy of all the registers so as to not update global variables all the time, which is usually fine. Like latency wise, that's not an issue. But what happens is updating global variables strips the compiler, the backend compiler, a lot. Like it doesn't know, if it doesn't see the definitions, it doesn't know what it's updating. It cannot do code aliasing stuff. It doesn't know if these two global variables alias for whatever reason. So what it ends up doing is not optimizing it as much. But if I make local variables out of it, it can promote it to registers, and it will actually map NES registers to the target registers that we're compiling for. And that makes things easier. But what it also means is if you're ever leaving the function, those registers need to be sort of flushed out into the global memory. So we do that by just calling the sync registers out function. Oh, I don't have C tags. Interesting. Yeah, not this one. Yeah, so if we go to the sync registers out, it basically just copies from the context. This context has a bunch of dynamic variables. It copies the registers out into the global variable, which are defined somewhere. Let's see. Yeah, they're defined here as global variables in the generated code. So it just assigns them back, and then we can exit. So yeah, and then we can return the address that we want to jump to. I think we have implemented all the instructions this way. So for example, if you have an exit instruction, which basically just stops the execution of the program, we just return 0. 0 is a special value. It indicates that we are done execution. Please don't run it anymore. And then we have, we also have RTS, which is like basically return from subprogram. So it's like the equivalent of a return instruction in x86 or any of the other assemblers that you've used before, which means that it pops the address of the stack and then jumps to that location. That is also a dynamic value, so we cannot normally jump to it, which means we have to sort of compute the return address from the stack by looking at the stack pointer and then sync out the registers and return. This actually can be optimized. We can oh, frozen frame. Is it better now? Let me check on my phone if I have frozen frames. No, it seems to be working fine for me. So I think it might be something on your end. Anyway, yeah. So we have a couple of these return. Yeah, so we just have, I think, 2 instructions that return dynamic values, which is one is indirect jump and one is this. Oh, we also have BRK. What does BRK do? Let's look at what BRK does. I have this handy file which explains force break. What does this do? Force interrupt PC plus 2 to SP. I think this is basically like a this is like a software interrupt. So it basically just yeah, I think it's if I remember correctly, this is just the set interrupt 1. So this actually just jumps to a predefined interrupt handler, which also is from memory somewhere. So yeah, it's stored at this specific address 0xFEFF. So I must have looked at the manual before. Yeah, again, this cannot be implemented directly by a jump, so we have to return out of the execution and then call the compiler again. But yeah, this is fine. So I think what we're gonna do next is just implement this loop of the pipeline where we constantly sort of emulate the code and run it, and then we will just start loading our actual ROMs. I think I have like I think I have some ROMs lying around. If not, we can download some from my old repo and then we can test it out. I think I have like Mario Kart and Donkey Kong. We can test those. Okay, so let's implement a pipeline.h, which actually will implement the whole pipeline for our What convention are we following? NES. I guess we need emulator.h. Which has all the types and everything and has the emulate code function. Okay, so I guess the main function we need for now is run main loop, which should also take the same interface, something like this, which should accept the offset, it should accept the program. Yeah, so let's do that. NES word offset. No, but we also need the program. So program is just an array of NES bytes. Perfect. Yeah, I think this should be good enough. We might also need to. You might want to allocate the memory outside actually, if you want to keep the state around. Eventually, that will be wrapped into some sort of like execution context, which we can accept later. We can change the interface. We can start with just. So we have this DNS byte adder D main memory. Let's take that as. Let's not call this program. Let's call this main memory, because this is where the whole sort of loaded ROM would be supplied in. Okay, so the run main loop function looks like this, and then we're gonna do pipeline.cpp. Hello. Welcome to the stream. We are working back. We're back to working on an NES emulator. Just talking about how we will implement jumping to dynamic locations at runtime, because we can't do that in build it. Okay, so let's implement this function. The first thing we would be doing is actually just moving a bunch of code from here. So establish a context. Actually, no, we need to have a loop here. So potentially this offset could be 0. So let's do a do while. Right, so we stop when offset is 0. For each of these, we actually call, yeah. Okay, so for each of these, we establish a new context. This is important, by the way, in build it. Every time you're trying to extract a new function, you have to create a new context. These contexts are sort of like consumables. That's just mainly because the context also has a lot of state inside, which gets updated, and you don't want to have like a state from the old execution lying around. I could potentially add like a reset function to the context, or every time you sort of call extract, it will automatically reset. But I don't want to do that because of debugging reasons. Like sometimes I do want to inspect the state afterwards, and I like to have it around. So the API is that one context per extraction. So we establish a new context. I have these two members being set here. What these basically do is this tell the build-it compiler sort of call to include some extra flags, or to include like some code at the beginning of the generated code. So dynamic header includes basically says when you're generating the code, please insert the string at the beginning. This has like my headers or declarations or whatever you want to sort of put into the file. And the second is dynamic compiler flag. So it just says when you invoke the compiler and the linker, in this case, it links and compiles together. Please add these flags to it, because I mean, in this case, it has like bash I runtime, tells it where the runtime logic is, it tells it where the runtime libraries are. Yeah, and NES runtime to tell it like, okay, actually also link in the runtime that we have written. So yeah, that's the purpose of these flags. And then I basically just call build it by saying compile function with context. So it says here's a context, here's a function, compile it with these parameters. I'm actually going to change the indentation for this. Yeah. So yeah, it compiles the program and returns a function pointer. So first thing we're gonna do is make sure that function is not null, right? Like technically it should complain inside. I think build it internally asserts that the function pointer it's returning is not null. It doesn't hurt to assert outside in case we don't have build it compile with debug or something. It's good to assert here. Okay, so we have we know now that we have a function, so we execute that. But before we execute, we need to allocate memory, and that should happen only once. So I'm gonna move this. Wait, I've been writing the code. Oh, I've been writing in .h file. Yep. Anyway, let's move it here. Apologies. Okay, this should just be NES byte. Yeah. So we have our memory allocated once and initialized to 0. I think the if I remember correctly, the MO6502 or at least NES doesn't expect the memory to be initialized to anything like sort of fixed. It can be initialized to anything. There's initialization on registers if I remember correctly, but nothing for the memory. But it doesn't hurt for us to initialize it to 0. I mean, it's how much? It's like 4 kilobytes of memory. Who cares? No, not 4 kilobytes. How much is that? How much is that actually? No, you can just test it here. 0x1000. Yeah, that's 64K. Okay, so that's not a lot of memory. It shouldn't hurt to initialize it to 0. Okay, we also have to initialize the registers, which is a runtime function. So that goes here. Great. And then we actually invoke this. So yeah, so we can say we can just update offset equals to func of main memory. Let's call this something else. D main memory. Actually, it's not D main memory. It's in the execution context. It's a very it's not dynamic really, but it's okay. At least it makes the convention clear. Okay, so we have our function executed, and I guess this is fine. We can keep this around, so we can check if it runs properly. Okay, now I'm gonna do yes, run main loop program offset is 0 in this case, and the main memory. Okay, so I did say that we're gonna allocate it outside. So this goes here. Yeah, this just lets us like inspect it outside if needed. Okay. So this should just compile now and produce the same output as before. Nothing should change, and then we will test out an indirect jump if that works properly. It was not designed. I guess there is no red now. Okay, undefined reference to NES main loop. I think I know why that is happening. Yep. I'm keeping this manual for now. Usually when I write make files like this, I use wildcards to look at the source files and do it automatically. But for this one, we're keeping it manual. Intertext is not declared in the scope. That's because we don't have runtime. Okay. Does this actually need any build things? Not really. So this can go into pipeline. Program was not declared in the scope. That's the last thing. What do we call this? Oh, come on. Huh. Oh, yeah. So wait, why is this? Of course. Now that it's actually executing, these are not dynamic values. These are normal addresses. Okay, and that should fix it. Add some debugging to make sure that it's running properly. Okay. Undefined reference to run main loop. Which is as OBJ is linked in. I'll make a mistake in the name. What's that? Find reference to NES run main loop. Oh, the types don't match now. I'm surprised it didn't complain. Okay, let's there we go. So this is working fine. We have the accumulator fast debugging for real. I've written build it code for the last 5 years. Reading those build it type errors is not that hard now. I actually say this a lot. How are you switching between terminal and Vim? I'll get to that. I'll explain it. So I say this a lot when I'm working on my C++ projects, part of my research, or just like when I'm doing something for hobby. When I run into segmentation faults, I'm actually really happy because debugging segmentation faults at this point has become easy. I know exactly what needs to be done. Like if I know there's a memory error, I mean, okay, if it's a nasty memory error and like some in some like parallel code that I write for research, that's a different issue. But if I'm writing like a compiler and if I get a memory error, I more like 95% of the time it's gonna be easy to debug. But if I get a compile error because of either like some type error from some weird template issues that I've made, because I write a lot of template code, metaprogramming, build it internal is based a lot on templates, and if I get an error in that, then it's just like reading walls and walls of error messages and trying to figure out what exactly went wrong, and that takes more time. It also means that if I can get a segmentation fault, it means my code compiles, which is usually the harder part in the kind of code I write. So yeah, those debugging things, the perception has changed for me a lot. Like 10 years ago, if you asked me, hey, segmentation fault, how does that make you feel? I would be, obviously it makes me feel annoyed because I do not know what's going wrong. But now it's more of like the habit has changed. But anyway, yeah, so there was a question in the chat, how are you switching between terminal and Vim? So here's what I do. Here's my workflow. I've talked about this in my very first stream, but I don't mind going over it again. So I use tabs. I have one session of Vim running. So I just have Vim opened once, and I open all my files as tabs in there, so like this, and I have some nice shortcuts to switch between tabs and move between tabs, but I never close this Vim session. So if I ever want to go back to a terminal, I just hit Control Z, which, if you know, in Bash, at least I guess it's a Bash specific thing, or it's a Linux thing actually, because that happens from the TTY. Anyway, digressing. When I press Ctrl Z, it sends the current process into background. So that actually sends Vim into the background. So if you can see here, it says one process stopped, one ID stopped, Vim emulator.cpp. So it sends my Vim into background, which means it's still there, but it's in the background. And now I can run my normal commands like compiling and executing and so on. And when I get back to Vim, I just do FG, which is if you know, in Bash, FG is for foreground. So it brings the last process in foreground. You can, if you have multiple stop processes, you can specify which one to bring in foreground. So in this case, I can say FG1. It'll bring Vim back. If I have like something else running, like say I have let's say I have Python interpreter running, and I hit Control Z. Now I have two processes in the background. So I have one Vim and two Python. So I can bring back Python back by hitting FG2, and if I want to bring Vim back, I can say FG1. And it's really handy. I've learned this trick from one of my lab mates. The very first time you see this, someone doing this, it actually feels wrong. Like, it actually feels wrong sending Vim into the background, but it improves your workflow so much better. Like, I don't have to switch between terminals. I don't have to like go to another window or anything like that, and it's so much convenient, especially when you're like working on, say, remote machines. I'm sure, yeah, there's definitely like solutions using Tmux you can use, but I like having my sort of my terminal and my editor in the same session. So if I sort of like set some variables, they'll be accessible everywhere. If I decide to do like this way of running make, that also runs in the same sort of space as where we are, and so on. So I've picked up this habit, and it works fine for me. Give it a try, see if you like it. But anyway, so to kill this process, oops, sorry. Yeah. So, okay, so we have our code compiling now, and we have our pipeline running. I'm just going to print, every time this returns, I'm just going to print something so that we can make sure that it's working properly. So actually, I'm just going to move this print statement here. Sorry. Okay, so in this case it returns 0, and 0 is a special case where we stop, so everything is working fine. Now I'm going to change some instructions to actually have an indirect jump, and let's see if that works fine. This is going to be messy to implement just because the whole thing with like you have to basically encode the program as these instructions. So this is our first exit, right? This is our you know what, let's just actually write this properly. Let's put comments. Okay, so A9, what is A9? It's load immediate. So this is not fun. So this loads 0xAB into the accumulator register. What's the next thing? 0xAA. I think this is just like an increment or something. Oh, it's just TAX. So increment, no, sorry, transfer A to X, not increment. So this is gonna be TAX transfer. What's the next one? E8. Yeah, it's just increment X. and this is exit. Exit is actually not a real instruction. We created this by using one of the unused opcodes in MOS 6502 just to help with emulation. The real ROMs, when we actually execute games, when we run games, they will never exit because they run in a loop forever, which is fine. They never have to hit this exit. But for testing, it's so much easier. Okay, so we have these instructions written down. Now what I'm going to do is I'm actually going to write and by the way, that's the reason the output is accumulator is AB and X is AC, because our program is just doing load AB into A in the accumulator, then transfer that A to X, and then increment X. So we get AB and AC. But anyway, so what we're going to do now is we're going to write a separate program which does, again, let's write the comments first. So let's say LDA 0x, let's say 55 for and then let's transfer to Y, transfer accumulator to Y, why not? And then let's do DEY, which decrements Y, I assume, if I remember correctly. And then actually we can do exit. So now what's going to happen is we have to first fill in these instructions. Oh boy. Okay. So 0xA9, the opcode first, and then the value. So this, good. Let's look at what TAY was. TAY was A8. So 0xA8 should transfer it to Y. Is there a DEY actually? There is a DEY, which is 88. 0x88, and then the actual exit. And now what we're going to do is we are actually going to change this ext into a normal jump first. Let's make this a normal jump, not an indirect jump. So JMP absolute, it just takes the format is it takes a 2-byte address, 4C, and then jump. So let's do that. 4C, and then it takes a 2-byte address. So what are the addresses going to be? So this is 0. Actually, this is going to be 0000 if you're writing it in hex notation. 0002. This is going to be 0003, right? Yeah, 1 byte. Now this one is going to be 0004, and this actually is going to be 2 bytes. So it's going to add 3 more. 0007, 0009, 000A, and then 000B. Okay, just filled in the addresses of where we are going to jump, and that gives us the absolute address 0x0007. Okay, but that's not how we encode it. The way it's encoded is you know what? Okay, so we have the address encoded, and this should technically jump to the LDA, and we should not get an indirect jump for now. But let's also print out the Y register. Okay, we are already printing out the Y register. Okay, great. Let's see what this produces. Of course. Wait, what? What did I miss? This is not how you write arrays. Oh, I think something is missing in. No. What did I do wrong? Okay, zero size out should be fine. Oh. Is the comment causing the issue? No, that cannot be it. What did I have before? I did have it same way. 0xA9, 0xAB. Yeah. Oh, this is the second part of the program, not the first. Oh, yeah, of course, I missed a comma here. Oh, yeah, thanks. You saw it before I did. Yes. I was looking at the long instruction. I was looking at the first instruction, so something was wrong there. Okay, let's run this and see what it prints. So we get ACC as 55, which is correct, and X as AC and Y as 54. Let's also quickly look at the code it generates. So the way Builder generate codes, it has this scratch directory where it generates a lot of C files, and they're compiled object files, and they're shared libraries, and it loads and executes them. Also, why the hell is there -03 in the name? That's a problem. I'll fix that. Okay, let's look at the latest file that we have generated. I think that's already fixed. So yeah, so this is the last file that we generated, and the code it produces a straight line. There is no jump here. There is no loop, branch, indirect control flow, because even though there's a jump in the emulator, that jump happens inside the compiler. So it doesn't actually generate, it just starts executing whatever, or starts emulating whatever is there at those instructions, and that works fine. So we have this temporary value loaded 171, then var1, which is sort of the regular, the ACC is set to that value. There's a bunch of shifts here. I think these are just like to set the bits for the flags. The good thing is the backend compiler can optimize this. This doesn't have to actually execute, because if we overwrite var11 immediately, the compiler knows that this value is stale, so it will eliminate that. And that actually is the reason why we are implementing this whole thing to generate C code, because now we can rely on backend optimizations to actually optimize it for us. And so, yeah, okay. So we have these flags set here. Then we have var2, which is x set to var1, and then we have increment on var2. var2 equals to var2 plus 1, and then we have what's next? Okay, so here's where 55 is loaded. So it directly jumps there. So it directly goes there. It assigns that to var1, which is accumulator, then does var3 equals to var1, which is the register y, and then does decrement on var3, and then it flushes out the registers and then exits by returning 0. So this works fine because we have a direct jump. Now let's try to change the jump to be an indirect jump. But that first means we have to set up the indirect jump targets and everything in the memory. So we will do that first. Okay, so this instruction now we want it to jump to 0004, which means first of all this address needs to be stored in memory somewhere. The problem is, okay, so we can just arrange for that, right? So let's load this value into the accumulator and write those bytes into memory. Actually, does sty take absolute? We can just do that if that works. Sty, oh, it does have absolute. Oh, but the absolute is for the address. No, sorry, sta. Yeah, store accumulator in memory. It does have absolute. Actually, we should be using. We can't use any of these. We have to do it manually. Okay, so let's load those values in the accumulator and then store them out. So again, comments first. LDA 0x00 in this case first, and then we will load the other value. So let's put 7 for now. This is going to change because once we shift the instructions, those things will move around, but that's okay. And then, okay, but we have to store this first. So we're going to store this at 0x. Let's just use the zeroth in the first byte for storing this. So 00 we can do, and then sta 0x01. Yeah, so this will compute the 2-byte address and store it in the first 2 locations of memory. And then we can just use an indirect jump to go there. So let's fill in these values. 0x A9 0x00, comma, I'll forget that this time. And then STA, what is the opcode for STA? STA absolute, this one is 80. So this also takes, actually let's use the 0-byte, let's use the 0-page version that only takes 1 byte of opcode. So that's easier for us. So that is 85. 0x85, we're storing it at 00. I'm sure there's a more efficient way to set this up, but you know, we're testing things, so it's easier this way. 0xA9, and let's put the placeholder value for now, and then store it at 0x01. Okay, now let's put the offsets for this. So this becomes 0004, this becomes 006, 0008, 000A. Now this jump is going to be an indirect jump. So indirect jump is also, I think, 3 bytes. Yeah, it's 3 bytes too. So this still, okay, first of all, computation for this. So BC, and then these will be C plus 3. Oh god, C, D, E, F. So C, D, E, F. F is 3 bytes. F plus 2 is 1, 1, right? Yeah. And this goes 1, 2. 6, 1, 3. Perfect. So we have our offsets, and now we can actually put that offset where we go. So we wanted to jump to 0x000F. So that's what will go here. Great. This should do something. Okay, so what we have done again is we did the first part of the program, LEA, TX, INX, and then we set up the memory to store the jump address, and then we are going to do the actual jump. But this time we are going to do an indirect jump, not an absolute jump. So that 6C and then upper code. So this gets 6C, but this also takes the address. So the address is going to be 0000, because that's where we have stored our that's where we have stored our jump target. Let's see if this works. 6C, right? Yeah. Oops, wrong directory. Yeah. So this is what happens when you keep switching between tabs and Vim. Hey, it compiles. Great. So good. We have something. We have. We don't have the correct thing, but we have something. So the initial execution returned 0. and then it returned F00. That seems wrong. If the function did return 0, why did it run again? Okay, let's debug this. Okay, so this is returning 0 in the first case. Execution, we don't have an exit anywhere here, right? Yeah, the only exit is here. It's funny though, if it returns 0, why didn't it stop? Oh, amazing. Put this before this, it should be after. That's the reason. Okay. But that still doesn't solve the problem that the output is wrong. We will fix that. Okay, so now we have the first execution returning F00, which is the wrong address because it should be 00F. Maybe we set it up wrong. Yeah, we stored it. It's in the wrong order. This should be F and this should be 0, right? Because it's encoded in different endianness. Can't remember which is which. Okay, let's see what this one does. Okay, so this one returned F and then return 0 in the final execution, and this time we have the right values. So ACC has 5, X has AC, which is what we had left before, and Y has 54. So the execution did actually go on the right way. And to now check this, if this produced 2 different executions, we're going to go to build it. We're going to go to scratch. You know what? Let's just delete everything. Let's clear the cache. And then do, this is good. Okay, so this time we have 2 C files, which is great. Let's look at both of them. So these are generated randomly by the names. Okay, so this is the first part of the program where we have 171, which is the AC loaded and the stuff with that. And then here is the part where we actually store the values into the memory to sort of create the address. So that happens, we load 15, which is F, and then we load 0, and then we store that in memory. And then here is the part where the indirect jump happens. This is where it loads the lower half of the address and the higher half of the address, concatenates it into var19, and then it eventually returns var19. So var20 equals to var19 and then return var20. So this is where we sort of like telling the execution, okay, I need to jump to this new address, which I know now because it is at runtime where the memory has real values. Now you would say, why would I not know the value in the compiler? Because it's a simple case. We wrote instructions which have constants encoded into them, but these could sometimes be calculated. Like usually when they write big programs, these values are computed through some computation. We do not want to assume that we'll know the value. We'll try to optimize it if we can, but yeah, so then this returns 20. So now this 20, let's see what the other file says. 506. And this is where the rest of the program is. So again, it loads all the registers as before, and then does the rest of the program, which is 85 and the decrement part and so on. And at this point, it returns 0 to say that the program has executed or ended. If you want it to run forever, we could also just to mess with the system a little bit, we could do the same instruction where we say, since the memory is in the right space, we can just do this, right? So this time it's not going to exit. It's just going to keep on constantly looping back and forth. Yeah, so it's constantly running now and compiling a new program and just jumping back in again and again. Ideally, we would not want this to happen. Like we want to have a code cache, which is what we'll implement now. If you look at this now, yeah, it's full of C code, which are all going to be similar because we just compile the code again and again. So the next thing we're going to implement is to actually have a code cache. I'm going to keep this instruction around to test, but let's go back to having exit. Okay, so for the pipeline, we need to establish a context. Class NES context. Actually, no, I think we already used the name NES context in the emulator. That's NES context T. So let's call it execution context because execution context T. So what this maybe let's use a struct. Yeah, it's fine. It's the same. Yeah. So what this execution context is gonna contain is all the state of the execution. So this one object we can pass around and it will take care of making sure everything is in sync. So the first thing it's gonna have is the offset itself. So NES word offset. This is the current location at which we are executing. So now we will start packing things into a struct. The second thing it's gonna have is the main memory. So NES byte star main memory, right? And then we're gonna have NES byte D main memory, which is the memory for execution. These will actually be same because once we start emulating, the program and the code are in the same address space, so they will just point to the same memory location. But it's okay to have them differently, so that's fine. And then we will have the registers are global, which is fine. We don't need to mess with them. What we need next is the actual program map. So that's gonna be a C++ map. Right. So it's gonna be a map from let's see. It's gonna be a map from NES offset, NES word, which is offset, to a function pointer. The function pointer has a weird type, so let's figure that type out first. Let's type def it. Type def. Oh god. NES program T. So it's a function pointer that tells us the address of what we want to execute. So we can use NES program T, which means this pipeline also needs to be casted to NES program T. Great. Okay, so this has a program map now, which is initialized to 0. So what we'll do is we will maintain this map and we will sort of insert program counters or program function pointers into this map once we have compiled them, so we don't have to compile them again, at least in this execution. And later we will add caching, which will make sure that it doesn't do it across runs too. So let's add some functions, some helper functions for this. Let's do NES program p get program ptr NES offset. And what we'll do is we will implement the logic of compile and look up into this get program ptr. So that goes. Actually, this also can be a member function now. So it doesn't have to accept any of these things. These are just there. Okay. So get program ptr. Let's implement that. First of all, this becomes execution context t, and then we have NES program t get program ptr, which is, sorry, where is it? Ah, here it is. NES offset. Okay, so the first thing we're going to check if this offset already exists in the map. So if program map dot find offset is not equals program map dot end, then we can just return program map of offset. Right? If it's in the map, just return it directly, so we don't have to recompile again and again. If it doesn't exist, then compile it. So now we can move this here. So this goes here. I'm gonna call this okay, so we create a new context, we compile the program, we have the func created from, this is the builder context, emulate code, main memory offset. Looks good. And then I'm gonna say program map of offset equals func, and I'm gonna say return func. Right? Okay. So we initialize registers. So this is going to change now. We don't have any of these anymore. It's just going to be void. Inside this, we're going to change it to program offset. Program offset. Okay. So first of all, we get the function. So we say auto func equals get program ptr of program offset. Right, so this is just going to directly give us the program offset, either compile it or fill up from the map if needed. And where did that printf go? It should be fine. We're not recompiling anything again. Okay. Program offset equals to func daemon memory, and this executes fine. Okay. Just need to change the driver to actually use execution context now. Should make a constructor. Come on, learn to type. Okay, this is good. So this takes program, this takes, no. Program offset first. We could also make that calloc call inside, but that's okay. You don't need it for now. Of course. Oh, it's a mismatched bracket. This doesn't need to be there. That should be good. Cool. NES offset has not been declared. It should be NES word. One error at a time. It's not a static, of course. So but that's a declaration. What? Okay, great. Build and use compiler. Yay, it returns the right things. Okay. Let's remove everything from that directory. And this time, let's see if we change our instruction to do bunch of indirect jumps, if it compiles it again and again. And this time it shouldn't. This time it should it'll still run in a loop, but hopefully, okay, yeah. So see, it's running much faster, and it's running much faster because it doesn't have to compile again and again. If we look at our Scratch directory now, we can see that there's only 2 files because it's just taking the same pointer and running again and again. So this is the behavior that we wanted. So that's good. Now let's go back to actually loading the ROM and doing stuff with it. Okay. So the first thing I have to do is actually download a ROM. I think I have ROMs lying around. Yeah, I think I should have some here. Perfect. So there we go. We have Super Mario Bros. And Donkey Kong. So I'm gonna actually just make a... I don't like committing binary files, but I think these are fine because these are resources. So let's do the Super Mario Bros. I'm gonna call it SMB. Perfect. It's a 40 kilobyte file, not too big. They wrote an entire game for Super Mario Bros., including all the assets and everything into a 41 kilobyte program. Our goal finally would be to actually convert this whole thing into C code. So as we interpret the program, it will produce a bunch of C files, which we can then ship as a game. We can say, look, here's a bunch of C files. If you compile them and if you run them, it plays Super Mario Bros., which I think is a fun side product out of this project. Okay, let's try open actually. I'm not gonna bother opening this file, but if I do open, it's binary, so it doesn't really make sense. But that means we have to load this binary and write a sort of, we have to write where the memory data is, where the instructions are. We need to start loading it. So I have written that before, so it was a long time ago, so a lot of like remembering things, which means we need a new include file first, which is loader.h. Sorry, NES loader h. Okay, so this one will be actually responsible for loading the ROM. This time I'm going to start by creating an object that we can load. So let's call it ROMT, right? So what does ROMT need to have? ROMT it will basically internally allocate some memory and load the file by most probably like mmap. So yeah, let's just map the whole file. So let's have a NES. Actually, should I use NES byte for this? It's mixing up terminology. You know what? We're gonna use char start for this file mapping. Okay, so this is where we are actually going to load the file. We're using a map. Let's write a function for that. Ooh, accidentally call it roller.c. We don't do that here. What do I do? Okay. So loader had load file, right? So void ROMT load file. Which means we also need to string, what? Hash include strings. What the hell? Why can't I remember this? Strings? Does anyone remember? Should be somewhere here, right? It is string. Great. Embarrassing. Okay. So this is good. Okay. So the first thing we're just gonna do is mmap the file, which means we first need to open the file. So this is gonna be a bunch of C code, not C-ish code. You know what? Let's man open. Yeah, we need the file descriptor, so that has path name, flags, and mode. Flags. We just need read only, so that should be fine. I think flags can just be 0, and mode can be come on. What? Oh, they're all concatenated together. So mode can be 0, flags can be O_RD. Okay. fd equals to open file name dot c string. What's the header for this? FCNTL luggage. Okay, so let's assert that f is greater than or equal to 0. And make sure that it opens something. We should print errors, but let's do it later. Okay, so we open the file and then we have to map it. You know what? I'm just gonna close this. We will use a map. Okay, so address size, length, prot, flags, FD, and offset, which means we first need to find the size of this file. So I think this is how you do it. You this uses file stream, not a file. Oh god. Okay, so we have to first get the size of the file. Jesus, I'm gonna write a helper function. I could use fstat, but it's fine. I like this version better. Path name mode I think usually is just R. Yeah. And then you do fseek. Oh, first third. Okay. Okay, so you take stream, offset, and whence. So offset will be 0, but whence will be fseek underscore end. And then you get the offset, the size, which is unsigned int. Actually, no, should be using size t. Should I be using size t? Not sure. There's probably a f size t somewhere in the standard. Oof. Okay, size t, file size equals ftel. Yeah, so what this does is opens the file, seeks to the end of the file, and then asks, where am I in the file? And ftel doesn't take any other parameter, if I remember correctly. Oh, yeah, it just takes the stream, and then it tells you where you are in the file, which gives you the size of the file. And this is a pretty standard way of actually determining the file size. Close the file, and then we return file size. Okay, great. So now we can start mapping it. So you know what? Let's just do this first. Size t file size equals get file size file name. Okay. So we have opened the file, and now we're gonna mmap it. So mmap actually so it takes a bunch of parameters. It takes the address, it takes the length, it takes the prot, which is protection, flags, FD, and offset. We actually don't need to specify the address. If you don't specify the address, it returns an address for you. We do not care where it maps, so we are not going to specify the address, but we are going to specify the length. We want the whole file to be mapped. Prot is, we just want it to read, right? No execute, no write, none. Yeah, so prot read. Flags would be just 0 in this case. Do we want map shared, violet, private? I think it's just going to be private. But we're not modifying the file anyway, so it's okay. It doesn't matter. We can just put 0. And then we have FD and offset. Okay, so let's do that. Let's do unsigned. Actually, not unsigned. We have a member for that, which is file mapping. File mapping equals mmap 0. So actually 0 null. So C++ 0 would probably not implicitly convert to void star, if I remember correctly. And C it does. In C++ it doesn't. Yeah. Okay. mmap. What is it? Size. So file size. Then prot. So prot underscore read. Flag 0. What was next? You know what? Actually, we should do map shared. And then it was FT and then offset. If I remember this correctly. 1, 2, 3, 4, 5, 6 arguments. 1, 2, 3, 4, 5, 6. Perfect. Okay, so we have a file mapping created now. We're also gonna assert Okay, so this loads the file. We still haven't done anything. We haven't parsed the file or anything. We'll implement the logic for that. But before we do that, we actually need to understand what the structure for this file is. So for that, I'm gonna say NES wiki. NES dev wiki. Yeah, this is a great resource, by the way. They have everything, including the format of the file, which is what we need to look at. So file format, NES. Is it INES? Yeah, .NES file format. It's the de facto standard for distribution of NES binary programs with use in licensed emulators, and this is fine. It is often called the INES format for the emulator called INES. Okay, so it has a header. NES was in name of the file format. This format is fine. NES file format. An NES file consists of the following sections in order: a 16-byte header, a trainer if present, 0 or 512 bytes, PRG ROM data, which has the actual ROM data, the actual program ROM data, and then it has the CHR ROM data if present. Then it has play choice inst ROM if present. Play choice, I think, is an extension for this for NES, where the cartridge used to have logic built in, which could extend like the CPU. We don't want to emulate that, so we will skip it. We'll assume that our ROMs do not have that. So for us, it's basically a 16-byte header. Trainer also, I don't think we would have. Actually, we might have trainer. Let's see. And then we have PRG and then CHR ROM. CHR ROM is where all the data is, including sprites and everything, and PRG is where the program is. Okay. So some ROMs additionally contain a 128-byte title at the end of the file. Oh, okay, good to know. Okay, so the headers. This is the header I'm assuming. Yeah, the format of the header is as follows. You have first 3 bytes, which is a constant. It always has to be NES followed by MS-DOS end of file. So we can maybe assert this to make sure that the file is correct. And then we have size of the PRG ROM in 16 kilobyte units. So yeah, okay. So we have 4 bytes, which represent the size of the PRG ROM, and we have, oh no, sorry, it's not 4 byte. It's 1 byte. It's at the 4th byte offset, and then we have size of the CHR ROM in 8 kilobyte units. As value 0 means the board uses CHR RAM. Oh boy, we will have to read about what this means. Flag 6, mapper, mirroring, battery trainer. Yeah, so there's a lot of like mirroring in NES, which is basically the same address space is mapped to multiple virtual addresses and so on, and that's done through like sort of mapping and mirroring. And we have to implement that. It's actually critical for most games. And then you have flag 7, which is mapper, VS play choice. I don't think we need this. Flag 8 is PRG RAM size. You don't need it. Flag 9 TV system, again not used. Flag 10 TV system, and then unused padding. So I guess all we need from the header is PRG ROM size and CHR ROM size. So we will get that. Okay, let's write a function called parse file. This parse file is not going to do anything. I mean, it's not going to return anything. It's just going to update the structure to have it. So this assumes that the file is already loaded. Make sure that you're not accidentally calling parse file. And this can be a private function, actually, but it's okay. So what do we know first need? The first thing we need to do is make sure that the first 4 bytes are NES and then MS-DOS end of file. So this I'm not going to actually assert. This I'm going to do it using an if condition because we want this to run regardless of debug or not. If not of file mapping of 0 equals n and file mapping of 1 I think it is, so it says 1A, right? $1A. I'm just going to check that. Let's just I'm not gonna error out here, but I'm just gonna return saying that something is wrong, you should not be doing this. You could throw an exception, but I don't like that style. Let the driver debug it. Oh, this means actually load file should return whether it succeeded or not, and so should parse file. So that way we can communicate to the user if it was fine. Okay, so normally this is gonna return 0. Let's return -1 here. Okay, and now we can actually parse stuff if it is okay. So what was it again? We have at the 4th byte we have size of program RAM in 60 KB units. Hey, what? It's 4th index, not 4th byte. Okay, so 16 kilobyte units. It can, yeah, it can be a large one. So let's just store it as size T. PRG ROM size. Right, CHR RAM and PRG RAM. Okay. Okay, 16 KB units, and then we have CHR ROM size equals to file mapping 4 into, I think that's 8 KB. So great. This looks good. The rest of the flags I'm going to, oh yeah, we need the flag 6 and flag, we at least need flag 6. That's a byte. Do we have a byte type actually? No. I'm gonna literally call it flag 6 because that's what the manual calls it. Oh, flag 6 equals. Okay, rest of the flags I'm gonna ignore. I don't think we need them, but if it comes up later, we can add it. Flag 6 is a very complicated structure. We'll get to when we actually need to set it up. Okay, so we have our parse file and everything done. Okay, so this should check now. Oh, this looks fine. Right, so we have loaded our file now, but we need to close. Wait, do I close the file? No, we don't close the file descriptor. Map needs to have it open. Okay, so this probably means you'd keep the FD around. Okay. Let's add this. Great. One by one. Okay, assert was not defined. That's okay. You can fix it. Okay. O_RD was not defined. What do you mean? There's no ORD? What? Why is it XTG open? How do I do? Oh, come on. How do I say this as a section? Yeah, it's just man. Oh, section comes first. Okay. What is the 3 right here? System calls? Okay, fine. What do I need? I need sys types and stat.h. Probably don't need both. Are you kidding me? What? Is it not RD? It's been a while since I've written this code. Oh, I think it's RD only. Yeah, I remember it now. Because why would any, okay, but prot read, no? Oh, missing header. sysmman.h. Alright, good night. I'll continue the stream for another hour and a half or so, and then I'll close, but you can obviously watch the recordings on YouTube or Twitch later. Thanks for joining. Alright, so this returns a void star. We don't have a convolution for it, so we need to convert this. Zero seven indeed. Control reaches an end of. There we go. It runs. Now we will actually load the driver. So what I'm gonna do now is move this somewhere else. Oh, it already exists. What's in the sketch? Let me find it. Test. If I ever need this, I'm gonna have to pull it up again. I wanna write it again and again. This took a while to write. Okay, so now we're going to load the ROM first before we do any of this nonsense. Actually, we don't need this for now because we're not executing it. We're just going to load the ROM. So NES ROM t-ROM. First we need to now assert that we have it. So if argc is less than 2, Don't have usage. Okay, now we can ensure that it's there, and then we can say t.load file. So this should at least work correctly. Let's see. Build NES compiler, ROMs, assembly arrange. Didn't error at least, that's good. And now what we're gonna do is just print things out. So we're gonna say PRG ROM size equals to %d. What is it? PRG ROM size. Just making sure that everything is in order. What side would I print this? X. Hey, so we have 32 kilobytes of PRG ROM and we have 1 kilobyte of CHR ROM. Amazing. And flag6 is 1. What does flag6 equals to 1 mean? So let's look at that. So 1 means it's this bit is set. Right? No, this bit is set. Jesus. Yeah. Mirroring. So 0 is horizontal, 1 is vertical. Okay. We will get to what that means later. And then we actually have none of the flags set otherwise. Okay, great. So this part is working. I'm gonna put this for now. And what are the rest of the flags? So there's a header, and then there is the actual. Okay, so somewhere it says that this whether we have trainer if present or not. Trainer is in flag6. So where does it say that? Come on, trainer. Mapper mirroring battery trainer. Lower nibble of mapper number. God. Trainer. How do I know if trainer is there or not? This is name table mirroring. How do I know if trainer is there or not? Trainer if present. It is not used on unmodified dumps of original ROM cartridges. Okay, so there's no way to know if there's a trainer or not just by looking at the ROM. But if it's an unmodified dump, then it will definitely not have a ROM. It will not have a trainer. So we will just assume that there is no trainer. I guess that's one way to deal with this. Okay, so then now what we need is we need an address to the PRG ROM data and we need an address to the CHR ROM data. So the loader should do that, I assume. No, the parser should do that. Okay. So we have PRG ROM size, and then we have find do I want to use, yeah, I can use NES word. No, it's not an NES word. NES byte. PRG ROM. NES byte star CHR ROM. Okay, so the parser is gonna pick them up. So the parser actually doesn't really have to parse anything, it just has to compute the address. So PRG ROM equals, it starts after the trainer. The trainer is not there, so it's gonna be file mapping plus 16. And CHR ROM equals file mapping plus 16 plus PRG ROM size. Great. So we have the addresses of our PRG ROM and CHR ROM. Perfect. Yeah, so I'm not going to look at any of the rest of the flags. I don't think they are required. Only flag 6, maybe flag 7 might be required too, but yeah. Oh yeah, upper nibble of the mapper number, so we do need flag 7. Flag 7, which is a 7 byte, I'm assuming. I'm gonna take just a 5 minutes break, get some tea. This tea has gone cold. I'll be back in a few seconds. In the meantime, I'm just gonna set to just talking. Yeah, I'll be back, folks. Yeah, it's really cold here today. I think the temperature outside is like minus 10 Celsius. It was at least minus 10 Celsius in the morning and feels like minus 18 or something. Coming to the office today was hard. Yeah, even now it's cold. I mean, it's cold. It's not cold inside the office, but you feel the cold. Like sitting next to the window, the glass gets cold and stuff. So tea helps. Okay, so we have our PRG ROM and CHR ROM. I think the PRG ROM is basically where the instructions are. Uh, so yeah, I think the way we would emulate this would be to actually just the main memory, just set it to the file mapping, and then specify the right offset, which is PRG ROM's offset. So yeah, we still have to like figure out a way to uh, translate these addresses between the NES offsets and the actual addresses. Um, I think it's not too hard, but or we could just like say PRG ROM as the main memory and then provide offset as 0. That could also work. We can just forget about those 16 bytes in the beginning. Doesn't really hurt us. Unless there are some things inside the instructions which are relative to the start of the ROM, which I don't think there is. Yeah, we can figure it out. Okay, so what other... Yeah, changing the scene. Yeah. Okay, so let's look at the PRG ROM and see how we can find the instructions out of it. Okay, so this has all the file format which we are good on. Let's go to look at this, tricky to emulate games. I think this has Super Mario Bros. On it somewhere because of it. Yeah, Super Mario Bros. Is probably the hardest to emulate game. And that's why the first time I was doing it, I picked that as the game I want to emulate. I got through most of it correctly. I think there was one thing that I couldn't sort of get myself to implement. It was going to take too much time, so I just hard coded a constant in there in the code, and it's still there to this date, which I need to go back and sort of change it sometime. Yeah, the sprite zero detection, basically, that takes a lot of time to implement. And I did it in a nice way, actually. I tried to keep it as efficient as possible, uh, but yeah, Donkey Kong is pretty easy to emulate. Okay, so let's forget about that. Let's go back to where does the execution start? No, this is the actual CPU. Where is it? Where is it? Where is it? Mappers. I guess I have to read about mappers first. Okay, NES games comes in cartridges, and this is fine. The term mapper arises from the concept of memory mapping, translating memory hardware into CPUs and PPUs address spaces. Memory map describes which address corresponds to which physical locations of memory. Okay, yeah, so there is like a 2 byte value that specifies, or sorry, a single byte value that specifies which mapper it is using. There is like, these are just named mappers, and then you sort of like have to read about how that mapper works and you have to implement it. Like, for example, I think we'll be using this. We don't need the 2.0 mappers. There's like 255 mappers. Many of them are like unused. But for example, 000 is the INES mapper, which I think maybe an SMB might be using. And it has this whole specification of how it is mapped into memory. Okay, so we will implement this. But I need to first figure out where the instructions are. Okay, here it is. Common capabilities. Multiple mapping of the CHR and the PRG chips into the NES address space, which may be expanded by often bank switching, dynamically changing the map. Oh yeah, you can also dynamically change the mapping, by the way. Name table mirroring for CHR. We don't need to do CHR for now. I think it's literally here where the start of the address is. Yeah, so here it is. 6000 to F7FFF basic family only, family basic only, PRG RAM mirrored, uh, as necessary to fill the entire 8K IB window. Write protectable with the external switch. Where is the start point though? Okay, so let's implement this. You know what, just for sanity's sake, I'm just gonna make sure that I'm doing this correctly. Let's see what our mapper is. So the mapper is stored in flag 6 and flag 7. If we go back to our file reference, it was flag 6 higher bits is the lower nibble of the mapper number. Why is it so complicated? And then flag 7's again upper bits are the upper nibble of the mapper number. Okay, so let's just do the mapper number. Unsigned char mapper number equals, so flag 6 of shift 4 bits, that should give me the upper nibble, and then mapper number equals mapper number, or flag 7 actually I don't need to do this. Yep, so this is gonna give us the upper nibble, and that's gonna be okay. So we have the mapper number now. You know what, I'm just gonna print it off here, and we're just gonna implement the mapper number that we need. We don't have to implement all the mapper numbers. There we go. NES byte does not name a type. Great, so it has mapper number 0. That's good for us. We only have to implement mapper 0 for now. So what I'm going to do now is actually also assert it here, so that we don't later accidentally run a ROM that doesn't have mapper 0 and then get screwed over. Okay, so the generic designation NROM refers to this, the INES members NROM. The suffixes 128 and suffix refer to Nintendo's own, refers to kilobits by Nintendo's own, not kilobytes. Okay. So PRG ROM capacity 60K, 16K or 32K. Okay. PRG ROM window not applicable. RAM capacity 2K or 4K family basic only. CHR capacity 8K. Name table mirroring fixed H or V. Controlled by solder pads, *V only. Okay, so it has fixed name table mirroring, which means you don't have dynamic name table mirroring. Bus conflict, yes. IRQ, no. Oh, no IRQ. Amazing. It doesn't have interrupts. You probably don't have to implement interrupts then. Audio, no. INES mapper 00. This is easiest to implement. Okay. So, okay, PRG ROM bank size not switched. PRG RAM 2 or 4 kilobytes. So I think there's a flag which should tell us what the PRG RAM size is. Oh, it says how much you want to provide. So you want to provide 2 or 4 kilobytes of RAM. So I think what we can just do is separately specify the PRG RAM. allocate the PRG RAM and bring it into the address space. Right. I think one thing we need to also do is just allocate the whole address space, uh, which is not much. It's just 64 kilobytes, which we do that in the execution main loop, but it needs to be filled in with some things now. So we can do, yeah, okay. So PRG RAM, it says 2 or 4 kilobytes, but most emulator provide 8. We currently have the whole 64 kilobyte provided, which is fine. CHR capacity 8 KIB TOM, CHR bank size not switch CC, okay. And name tell mirrorings, okay. All banks are fixed. So CPU address 6K to 7FF, family basic only, PRG RAM, mirrored as necessary to fill the entire KIB window. What is a PRG RAM? Okay, 8000 to BFF is where the first 16 kilobytes of the ROM goes in, and then C00 to FFF last 16 kilobytes of the ROM. It's not contiguous. 8 to BFF and then C00 to FFF. If it depends on whether the size is 8 or okay. So how am I gonna do this? We need to allocate the whole address range, and so the PRG RAM is different from the PRG ROM. I guess PRG RAM is just the data. Okay, I'm a bit confused. Okay, so we need to pretend as if the addresses are at the offset 8000 to BFFF and C1000 and C000 to FFFF. Okay. Should we just copy the data over there, or should we copy the data over, or should we just keep the instructions the same? I think it makes sense to copy. Let's not keep like directly from the, we can optimize it later. So let's copy it for now. So what we're gonna do is we're gonna take an execution context which has the memory inside it, and then we're gonna attach a ROM to it. And attaching a ROM would just basically copy over the instructions at the right place, so it can start executing. So that's what we're gonna do now. We will have that pipeline, yeah. So we have execution context, right? It's gonna have a member for D main memory now, and this is gonna get allocated in the as soon as we load it. So yeah, the execution context itself is going to have the data. Right. Which means the driver doesn't need to allocate it anymore. which means the constructor doesn't need to accept it anymore. Actually, we don't need to accept main memory either. It's gonna be the same. And actually, we don't need a offset either. This all goes away. Yeah, we don't need any of this. The offset is comes from the mapper, so we will have an internal variable set by the mapper when you attach the ROM. So wait, no, sorry, what? Wait. Oh, I had it in the header. Okay, so this is done, and now we add a function on the execution context called attach ROM. So this is gonna take ROM D by reference. Yeah. So in the driver now, we're gonna say create execution context, and then execution context dot attach ROM. Why is it called T? So this is gonna attach the ROM, and this attaching of the ROM is then gonna copy over the data from its PRG ROM into it. Okay, so then we have to implement this function. Void execution. Sorry, I'm trying to wrap my head around the best design. It's not like I'm trying to figure out what the right sort of way of organizing this code logic is, like which part should be taken care by the loader, which part should be taken care by the execution context. It's like I'm trying to get the right design, and it just annoys me sometimes if it doesn't work out properly. I don't like changing designs later. I'm fine with changing implementations and optimizations later, but just like having to change where things happen is just so annoying. Yeah. Okay. So this first of all needs. Okay, so the first thing we need to do is copy over the program RAM into the right position, but that depends on the mapper. Yeah. If ROM dot, so mapper needs to be a global variable. Not global, sorry. Signcar mapper. Mapper number. Okay, so pipeline is gonna say if rom.mapper number equals yes, let's switch case this. Switch rom.mapper number case 0 default. std Sierra invalid or unsupported Okay, and in this we're gonna actually copy over the data. So if rom.prg ram size equals prg rom size equals 32k, so no, 16k first. Actually no, the first part should be copied no matter what. So mem copy into d main memory plus this value 80x8000. What are we gonna copy? The rom.prg rom comma 16k, so 16 into 1024. Okay, and second one is gonna be on size. If rom.prg rom size equals 16 into 1024, then it's mirrored. So then this goes here, but it gets copied here. Right? See? Yeah. Else we copy over the other half. Okay, so it copies over the instructions into the D main memory from the ROM. If it is 16, then it's mirrored. If it's not 16, then the rest half is copied, right? Last 16k of in ROM or mirror of this. Okay. That's right. And it also sends program offset equals to 0x8000, I believe, because that's where the execution starts. Yeah, and then the 6000 to F7FFF would be the program RAM, which it can use for its own computation. Let's just Google, look up NES program start execution. Okay, here we go. The CPU starts executing at the values it reads from FFFC and FFFD. Oh, where is this specified? Interesting. So, okay, this is where you get the offset from FFFC and FFFD. I remember something like this before. You know what, I'm just gonna keep this open, the old NES emulator, in case I have doubts. So that also had a similar NES decoder, no, file loader, yeah. And this probably sets somewhere start of the, yeah, here it is, mapper ID. Does the same mem copy, and then name table mirroring is set up, but I don't see where the start address is set up. Maybe I do it. Oh yeah, that happens independent of the mapper. That's right. So where is that set? This is all written in C, by the way. I should, and this new one isn't going to be in C++. At least the emulator. The generic code will be C, but yeah. Execution context might do it. Yeah, initialize. Where is it? Let us do the initial. Let's see. Identify reset address. This is the function. File loader. Yeah. Identify address in emulation mode. Yeah, so here it is. It does what that command says: 0xFFFC, and that's where the address is. Okay, I guess I'll do that. So I'll do it as part of the attach ROM itself. So we need to get the higher bits first. No, first the lower bits and the higher bits. So inside program reset lower equals unsigned char. We can use NES byte. PRL is equals to D main memory of 0xFFFC, right? Yeah. And then NES byte PRH equals to D main memory of 0xFFFD. Now we get program offset equals PRH shifted by 8 or PRL. Perfect. So this sets our execution correctly. And maybe now we can just do one loop of compilation and see what happens. Okay, so we attach the ROM, and now we can do the main loop. Probably gonna crash, but you know what? Learn from it. Well. Copy was not defined. C string. I just included it. Of course I read it in the right place, wrong place. Should be in pipeline. Okay. Okay. Now this should work. Perfect. And let's see what happens when I run SMB. Great. So emulator.cpp 637. We got an invalid instruction opcode 7. Why did that happen? We probably jumped to a location that's not valid. Let's figure it out why. 637 is probably just the default case. Okay. I think what we need to do now is start printing out stuff as to what instruction we are emulating, and we'll eventually find something wrong with it. The good thing is we have an original version to compare against, so that should help. Emulating instruction opcode equals %d/%. Let's call it 02x. It's gonna be a 2-byte value. That's quick. Too quick. Okay, so it didn't do a bunch of instructions, but then it eventually went to a bad instruction. You can also print out the instructions it's emulating. Actually, you know what, let's just print out. We have the instruction data, so we can just say we have opcode names somewhere, do we? Do not have opcode names. Huh. I thought I did it. Oh no, it's I thought I had opcode names. Annoying. Okay, I guess we do opcode names too. Hey, why did I not have opcode names? Not fun. Okay, so now once we have the opcode, we can just print out the opcode name from it. And addressing mode. Sure, okay. So %AS is to object, that should be fine. We'll also print the address it is at. So this is going to be a 4-byte offset. %04x. Okay, so it's going to be PC. And then it's going to be instruction dot, you have the opcode. So we can just do NES opcode names, right? Oh, this has to be static. Unless I put this into instructions, no, I don't put it anywhere. Okay. Names, yeah, of code. Addressing mode names. So here AM names. What's the instruction type? Addressing mode. kidding me? Come on. How do I do the addressing modes? In static const char star. Okay. I was worried I was gonna have to use std string on that. But oh, static var. Okay. Printf complaining about static var. Obviously it is. So PC is a static variable, but we want the actual value out of it, so you need to cast it back. Normally that cast is implicit, but not when calling printf, because printf is a periodic function. Oh boy, what the hell? Where? The addresses seem to be fine. The names are not right. Instruction NES opcode, names opcode. Oh, no. The opcode is the exact value. We don't want that. We want mnemonic, whatever that is called. The decoded thing. Oh, wow, it's called opcode. Okay, instruction.opcode. There we go. Something. So what do we have? SEI, CLD, LDA. So this looks correct to me. Like these instructions seem to be fine, because actually it's also starting from 8000, which maybe just seems like SMB has execution starting from the beginning of the instruction stream. So that's good. This seems to be fine, but then it suddenly has. It goes to 9070, so it's probably a jump somewhere. The jump is probably wrong. That's what is happening. Okay, we can deal with this. Yeah, there's a JSR ABS happening here. JSR is jump to subroutine. Oh, you have a BNE relative. Then you have null impl, which is an invalid instruction there. And then it has 7. So how does that happen? Is it possible wait, there should be a return somewhere, right? If it's a JSR. JSR is jump to subroutine, if I remember correctly. Yeah, jump to new location, saving return address. Okay, so this is JSR, and then that should have a RTY somewhere. No, what is it? RTS. Yeah, return from subroutine. Okay, I think maybe there's a problem with the decoding somewhere. Happens to the best of. Okay, so there's a JSR here. And it jumps to 90cc, does a bunch of things, then it has a null impl. Yeah, I think this is just decoded wrong. I think there might be an issue with BNE being decoded in the wrong way, which is causing. Yeah, I think that's what is happening. When BNE is happening, it's sort of messing up the PC a little bit. Emulator. I think the PC needs to be offsetted. Yeah, I think these branch instructions need an extra addition or subtraction at the end, because they don't jump. let's look at it. Branch or not equal. Oh wait, that is a related term. So it's an address calculation issue that branch or not equal is going to the wrong address. Yeah, so that E1 is going to 9070, which is probably wrong. Okay. Okay, we'll just read the thing for PNE and see how it's supposed to be implemented. Branch on result not 0. Okay. Branch on Z equals to 0. Cycles are an annoying thing. Add 1 if branch. Okay. It's a relative addressing mode. I think we just emulated this wrong. This mode is used with branching condition instruction. It's probably the mode you will use most often. Add a 1 byte value is added to the program counter first, and the program counter's execution continues from that address. The 1 byte number is treated as a sign number. That is, if bit 7 is 1, the number given by the bit 0 to 6 is negative. If bit 7 is 0, the number is positive. Okay, this enables a branch displacement of up to 127 bits in either direction. So this instruction will check if the 0 status if it is set, 39 decimals will be subtracted from the program counter and execution continues from that address. Yeah, the problem is we also have a increment at the end, right, which we need to sort of offset, but that only needs to happen if the branch is actually taken. So what are we gonna do at the end? We're gonna do PC equals to PC plus what are we doing at the end? Yeah, we're gonna do PC equal PC. But what if I just do continue, and if I just go to the next address, then it won't do that, right? Oh, I do have a continue. Amazing. Of everything. Okay, so why is it jumping to the wrong address then? PC plus equals to get relative offset and then continue. Yeah, it reads a 1 byte offset, computes the get relative. Okay, this is probably something wrong. Also, what am I doing here? Why? Compute the offset and then don't use it. Genius. I'm gonna fix this now. Yeah, probably the get relative offset function is wrong. Okay, if D and 80 return minus D and 0x7f, so this is gonna keep the lower bits, else return D and 0x7f. So it takes an unsigned char and it with 0x80. 0x80 is 10000, yeah. If that is the case, then it returns minus D0. That seems fine to me. Else returns D7f. Let's think. This is what it matches with the manual. This addressing mode is used with branch and condition instruction. It's probably the mode you'll use. 1 byte is added to the program counter and the program. Oh, okay. 1 byte value is added to the program counter and the program continues from that execution. The 1 byte number is treated as an integer If bit 7 is 1, the number is given by 0 to 6 is negative. The bit 7 is 0, the number is positive. This enables a branch replacement of... Wait, no, this should be fine then, right? Okay, and I guess what we do is also print out the offset. See what this does. I want to see what the byte was and what byte offset was F1. So F1 is 11110001. So it's gonna be 0B this and negative of this, so it's going to be minus 113. What was the original instruction? It was this. Okay, so it's going to be 9070, and that's what it jumps to. But is that not what it is supposed to jump to? I'm just gonna... Yeah, this is fine. I'll figure it out. So it's jumping at least correctly, but the problem is there's a null there. 9070. And then it has an invalid instruction. What was this 9070? Maybe I implemented this 9070 wrong. Let's just print the bytes. It's gonna be a 2 byte. Oh, so the jump directly has a 7 there. And 7 is not a valid instruction, I'm assuming. Let's check. Going to be annoying. Am I gonna ever find if 7 is a valid instruction or not? I mean, in my instruction table, 0, 1, 2, 3, 4, 5, 6, 7. Yeah, it is null. But does that mean it's actually null? It's tempted to... Oh, so it's feature expansion. Yeah, so it is an invalid instruction. Oh good, we have a table here. So why is it jumping here? Okay, so the instruction emulation is not... The null part is not wrong. What is wrong is it's jumping to an invalid instruction. Come on. Wait, there have been other BNEs before. And they seem to be working fine. Oh, when it's positive, it's working fine. When it's negative, maybe it's working wrong. Yeah. I think I need to read this properly. Yeah. This mode is used in branching condition. A 1 byte value is added to the program counter and the program counter continues execution from the address. The 1 byte number is treated as a signed number, that is, if bit 7 is 1, the number given is negative. If bit 7 is 0, the number is positive. This, okay, let's go to some examples. Yeah, it is right. 1001001111, and it's minus 39. Otherwise, it's plus 39. So why is my negative jump not working properly? Why is it jumping to an invalid instruction? Is it supposed to jump to an invalid instruction? Okay, here's what I'm gonna do. I'm just gonna check if the old emulator ever does this. Where's the ROMs? Super Mario Bros. And then build. Where is it? Translation auto. Okay. Oh, it's starting the whole thingy. I need to print what addresses are being emulated. So execution context.c here. Yeah. They should have a pretty printer somewhere, I think. If decoded instructions is good. Translating. Oh yeah, info log. I think the driver has a call to this pretty printer. Yeah, address decode and print from file. Nice. It has this thing which I can just put inside decoded instruction. There we go. So we have address minus base address. So it's gonna be to decode address minus base address, I assume. Okay, this is. Oh wait, we don't need this. We just need address because yeah, address is already unsigned long. Decoded instruction of name, AM, and argument. Perfect. So we can just compare and see if it's jumping to the same instructions. Addressing mode. So what is the addressing mode? Decoded instruction of addressing mode. Okay, so it did print a bunch of things. Should have probably piped it to a file. But these are all the instructions it's sort of executing and decoding. Please. Let's compare that to our output and see if it matches. Oh, this is long. Oh, I'm not gonna do this. I'm gonna kill the game and open decode.txt. Okay, there we go. This is what we wanted. And now let's compare it against ours and see where it diverges. Jeez, okay. So we have SCI, IMPL, this goes fine. Also, these addresses are wrong. Oh, it's the address of the basic block. That's okay, that's fine. The last thing I think we had was a JSR. Yeah, let's look for JSR. Which one is it though? Is it the first one? Is JSR 90cc? Yeah, 90cc. Okay, so this is the first one. Oh, but then it doesn't actually emulate that because it depends on where the execution goes. Okay, here 90cc. LDX, LEA, STA, STX, CPX, BNE relative 4. Oh, this itself is wrong. Unless it takes the negative branch. Okay, then it's fine. BNE relative 4 goes to... So this is taking the true branch of it. Right, yeah. So that's gonna go to BCS relative to, yeah, here it is. And then STY, DEY, CPY, BNE, F1. Yeah, perfect. Where does it go? So this ends up because this is not compiling ahead of time, right? This is doing it on the fly. So at this point, it knows whether it's going to take the true or false path, and I'm assuming it takes the false path. So it directly goes to DEX impulse 000. Actually, it's gonna end the basic block, right? It's gonna go till here, which we will also get to. It's just we have to take the true path first. So that will happen when the actual execution gets there. So when this executes, BN relative F1, I think what's happening here is just it's jumping out of the subroutine. Yeah. First of all, I need to change this to print the addresses properly. Just address, what is it? To decode address. It's to decode address plus size equals to size. There's some translation functions which do this. So I guess what I'm gonna do is to code address minus execution context of base address. I think this should be fine. Nope. File handle of address space start. So execution context of file handle of address space start. Sorry, this is taking a little too much time. I think the possibility is that it might never actually take that jump in the logic, and that's why they might have just put like a bad instruction there, which means that there's nothing wrong with our code. It just means that when we see a bad instruction, we just abort or put a runtime abort saying you have reached a point in the code that you should not reach. That might be the reason why this is happening, but we should investigate it. So this was at 90E1. Yeah, so it says a BNE relative F1, 90E3, and it actually does RTS here, so it returns from the thing. Does it ever take 9070 or 9071? Oh, it does take 9071. But that's from 906E going to 907. Nothing special about 9071. What about 9069? Does have that, but that comes from 66. So I think this 90E1 is never actually supposed to take the true path. It's never supposed to branch on not equal. Okay, so here's what we're gonna do. We're gonna change the logic a little bit. Instead of asserting in the emulator that you have reached a bad instruction, we are going to delay that bad instruction to the runtime. So if it ever takes that branch, then it will complain. So I'm not gonna have this here. I'm gonna say runtime. I do have a runtime, right? No? Where am I putting my runtime stuff? Emulator. I was putting it in the emulator. Okay. Okay. So I'm just gonna. Let's actually get a runtime namespace. So we're gonna have a runtime unreachable, which is a function. So it's gonna be builder var of type. Let's just make it void. That's okay. Equals no. This is gonna be extern. And this goes into emulator.cpp. Equal to builder as global runtime unreachable. Okay. Now what we're gonna do is the default case. You're gonna say runtime colon runtime unreachable jump to invalid instruction. Yeah, so this is gonna like at runtime fail instead of failing at compile time, which means this will only fail if it actually jumps to a bad piece of code. So this stops us from like failing on compilation for bad instructions. which means we also need to change our runtime to have the function. Okay. Okay, so that problem is kind of solved. So it did jump to 9070. Oh, we should stop execution there. We should continue. So how do we stop execution here? This is gonna say what to return from this. I can just do return 0 because yeah. Yeah, this will just return a 0 there, and that way it won't keep on executing ahead. Okay, this time execution actually went to an invalid instruction at runtime, but now we can debug this. Yeah, these are not valid addresses. It shouldn't be jumping here. Oh wait, this is our first JSR. It did go pretty far. Oh, this function just returned FFF0. Why? Probably... So an indirect jump or something? It seems to be running mostly fine now. Function returned FFF0. Why is this branch ever happening? I'm gonna take off some of the printing stuff. Yeah, it must have been one of the bad instructions. Which was the relative instruction that made this jump? Can't be JSR. This 90 NTCC stuff was done before too, right? Yeah, why is it decoding the same instruction twice? So JSR ABS 90cc has LEX here. I mean decoded. Why did it decode it again? Yeah, this seems wrong. Oh no, it's inlining. It's subroutine, right? Because yeah, there's no caching for if you jump in the middle of a code here. Okay, so that's fine. It just has two different pieces of code jumping to the same subroutine. Then what happened after 90cc? How did it? Yeah, what is the instruction after 90cc? Yeah, after it encodes 90cc, it should encode 90CE. Why did it stop here? Why did execution stop? Um, I think I know what's happening. This is built in doing its own thing. It's executing multiple times. So, um, I see. When it actually did 90cc, it realized that it's merging, and it probably previously have sometime had generated 90cc in this execution, and it just merged the execution. Okay, that's what happened. Yeah, that's why the execution stopped there. Where is the last in enter? Oh, it is the first one. Okay, so then it makes sense. Yeah, okay. So it's exploring both the sides. Okay. It says that I have seen JS 90cc before, so it just jumped there. Okay, that's fine. So the question is, why did this return FFF00? We could tell the execution environment where this jump came from by printing out the address. Yeah, we could, in the actual execution, we could print out which instruction is returning. That's right. Okay, so I need a runtime print now. Obviously, this let's just call it printf. It's okay. We need a special function. And this is just gonna be printf. That way it's easier. Okay, so every return Yeah, I'm gonna print f the PC that returning from address person 04x-n NES Word PC, right? Yeah. Has to be one of these. It's probably the RTS. Ah. Yeah, this is a bug in Build It that I should fix, where if I have escaped characters, I should like properly escape them, but in like dynamic strings. But for now, I'm just going to like manually escape them, and that should be good enough. Let's try to fix this. Oh god, implicit declaration of built-in function printf should be runtime.h. There we go. So this was happening from 7f93. What was 7f93? You know what? I'm gonna put this into a file. Seven F93 was we never generated code for 7f93. Interesting. Returning from address 7f93, but we never generated code for 7f93. How is that possible? Also, 7f93 doesn't seem like a valid address either. PC has been mangled. NES Word PC. Okay, it's definitely not this one, because this one returns 0. Could be this one. Oh, PC. Wait, is it a BRK? Okay, the PC is adjusted here for some reason. PC equals to PC plus 1. You store the PC. But I don't think we ever call BRK. Do we? Oh, we do BRK. Oh, 7f92. But 7f92 is not even valid code. Oh boy, okay. So why did it go to 7f92? 800D has a branch on relative PPL. 8000D. Okay, maybe go back to our old emulator. No, actually, you know what? We have decoding instructions here. Just look at that. So 800D somewhere, yeah, here. BPL relative FB. Okay, so I think this is easier to solve. What is happening is it's taking a jump that it's not supposed to take, right? Because 800D minus FB. So let's see, Python 0x FB. Its binary value is 1111, this one, and if I take the lower bits, I get this 123. So if I do 0x800D minus this, it goes to 7F92, which is what we did. But apparently 7F92 is not supposed to ever take, because our execution never went to 7F92. Yeah, the reference implementation didn't go to 7F92. So what is BPL? Let's check. What is BPL? Branch on result plus. Oh, I think it's just a matter of the instructions not implemented properly. Good. This is easy to solve. At least I think so. Okay. We could dump the value of registers after every instruction and check, but that's gonna be painful. Let's just look at the log. So we have SEI, CLD, LDA, STA, LDX, TXS, LDA, BPL. In this case, it actually goes back to 8000. How does it go back to 8000? Oh, that's our case, so just restarting the execution, that's okay. Where does it go in this case? BPL goes to LDA, which is 800F, that's fine. And then again a BPL. Why do they use these bad addresses for relative jumps? I don't know what these people are doing, man. Magicians. Right, so this actually executes till here. So this one does take 7F9. For some reason, this branch is being taken either here or here. Or here. No, not here. 7F92 is the one that's being taken, right? 7F92. Oh, there's only one. Good. There's only one occurrence of 7F92. So it's definitely taking this branch. Now, why is it taking this branch? Annoying. I should just manually evaluate these instructions and see whether it's supposed to take the branch or not, and then just compare the code and see what it's taking. Yeah, that's probably the right way to do it. Okay. SEI doesn't do anything as far as I can tell. It just sets interrupts, right? Sets interrupt disable status. That's okay. CLD does clear decimal mode. Okay, that's, please tell me it's not a decimal mode issue. Okay, okay. And then we have LDA 016. So it loads 16 into accumulator. You know what? I'm gonna manually just do this. A equals to 0x1 0x0010. Okay, and then it does STA ABS 20,000. So what is that address? Okay, so 20,000. So memory location 2000 has 16 stored. Okay, it's fine. LDX load into x 0xff. So x equals to 0xff. Also, this is wrong. You cannot load 2-byte values. What? Oh, it's pound. What was pound addressing mode? Hash. What was hash? There's some addressing mode. Yeah, okay. Oh, it always prints a 4-byte value. That's why. Okay. That's what it's, okay. So then A is equals to 0, 0. X is also equals to 0, 0. Sorry, my bad. It just prints all 4-byte values. Okay. And then we have TXS. So transfer X to what? Transfer X to stack pointer. Okay. So at this point, SP also equals to 0. Great. And then LDA ABS 20 equals to 20. Great. Oh, great. And then we have a BPL immediately. 00 FP. Branch on positive. Right? Branch on result plus. Branch on n equals to 0. Since we just moved 20, n is 0. It's not a negative number, right? Yeah. But wait, I don't think LDA sets flags. Oh my god, are they? Yeah, it does say, no, it doesn't say n. So branch is positive. LDA ABS 20. Sorry. So PPL relative should be taken. Branch on PL. If not of sign, then PC equals to relative. And sign is not because n is, it's not a negative number. Yeah, branch on result plus. So why is it doing this? It should jump to a negative address. Unless I've messed something up. Maybe the ABS version of LDA doesn't set flag. No, this is fine. Oh wait, no. It's LDA ABS 2002. So it's loading whatever is from 2002. My bad. It's loading from the address 2002. So, oh, I see. That's what is happening. Our memory is uninitialized. 2002 in there might have a negative number. That's why it's not jumping to. I see. Okay. So we get to go back to the mapper and see what needs to go at 2002. Okay, so this basically means there's no issue with our code. It's working fine. It's just we're reading from 2002 and branching on that. This value in our case, since we have just initialized everything to 0, it's just a positive number. So it does end up taking the branch. It's not supposed to take. In the actual NES, there's probably some data there which we currently haven't loaded. Our memory is sort of like not properly initialized here. And that's why it's causing it to take a jump that it's not supposed to take, which means I think we are fine in this. I'll just figure out what should go at that address range maybe, and then we can close for today and continue the next time. I don't see anything in this bank. Maybe it's picture memory? Yeah, maybe it's PPU. I haven't implemented PPU yet, so let's see what are the address range for it. Yep, it is the PPU memory. Oh, so we have to implement memory mirroring for this. Okay. Let's see. A name table is a 1024 byte area of memory used by the PPU to lay out backgrounds. Each byte in the name table controls an 8 by 8 pixel, and each name table has 30 rows, 32 tiles, and 60 bytes. The rest is used by the name table's attribute table. With each tile being 8x pixel, this makes a total of wait, is that 2002? It's actually 0220. Oh, it's a different address range. Yeah, but it's the same thing mirrored again and again, I'm assuming. No. Wait, that address was... You know the best way to see what the address was? We look at our generated code. Getting in the interesting... This does not seem right. Oh, I did not do LSLT. I'm assuming this one. Here we go. No, this is the last thing generated. Oh god. I need to find maybe this one. Yeah, there you go. So it's actually loading from 8194. What is the hex of 8194? It is 20. Okay, so it is 2002, not 0220. Okay, so yeah, what is loaded there? The NES has 4 logical name tables arranged in a 2 by 2 pattern. Okay, like this. Each occupies 1 kilobytes chunk of PPU address space starting at 2000 at the top left, 2400 top right. Okay, but the NES system board itself has only 2 kilobytes of VRAM called CIRAM stored in a separate SRAM chip in a for 2 physical name tables. Hardware on the cartridge controls address bit 10 of CIRAM to map one name table on top of another. Okay, vertical mirroring. 2000 equals 2800 and 2400 equals, okay, this is fine. Okay, but what is mapped there? I guess some sprite data is mapped. Okay, this is fine. I think we have narrowed down the issue. We will continue working on this the next time. I'm gonna quickly switch. Just talk for a bit. Yeah. So I think we made enough progress. We implemented a bunch of compile, load, execute loop, and I think we are seeing the correct behavior that we are supposed to see. We need to start sort of like filling up the memory correctly now, and hopefully we will soon have like our instructions executing in the same order as they were executing in our previous emulator, and then we will switch to implementing the PPU so we can finally draw some sprites and actually see the game running. Okay, I think I'm gonna stop here for now. We'll continue next time. Thanks for joining. I'll share all the resource. I mean, I don't think I have anything to share today from the resources side. I'll just maybe wiki, NES wiki, and the pages where we found information about the mappers and stuff. I'll put it into the doc and push, and also push changes to this code base. Clean it up a little bit, remove some extra comments that we had, and I'll push changes. All right, thanks everyone. I'll post this on YouTube for later, and I'll also announce when the next stream is happening. Thanks.